Hello, everyone. Welcome back for another episode of Cosmic Pie. I am Robert Moore, and with me today is Professor Dean Smith.
Hi.
We're here at the wonderful campus of the University of North Dakota. And let's see, what else should I mention? We have a live chat, so if you have any questions during the show, please let us know, and we'll do our best to get to them and answer them. So, one more thing. I need to disclaim. I need to mention that the opinions expressed here are solely those of myself or Dean, and that they do not necessarily reflect the opinions of the state of North Dakota, the University of North Dakota, the Department of Physics and Astrophysics, the College of Arts and Sciences, and so forth. So, now that all that is out of the way, how are you doing today, Dean?
I'm doing pretty good.
Excellent, excellent. So we're going to be talking about, starting off talking about things that are up in the spring sky, I think.
Yeah, I figure do a little tour of the sky. I like to know where things are in the sky that we talk about.
Absolutely. I mean, we talk about all these things. It's like people are like, where are they? So
yeah, these are real objects.
Right.
They're not just pictures on the internet or the textbook. They're real things. A lot of them you do need a telescope. Some you need a pretty good sized telescope, but
right.
a lot of these are within amateur realm of seeing. So
And I like that you point things like that out. I got to admit. You don't need to see a lot of this stuff. You don't really need a big setup or a big rig. Like you can see the cloud bands of Jupiter and the moons of Jupiter with a pair of binoculars, and the rings of Saturn with binoculars. So there's a lot of things that you just don't need a huge rig and setup to work with and be able to see for yourself.
yeah.
So
Yeah, even just a small little 2 or 3 inch aperture telescope will give you a good view of Saturn's rings, Jupiter's moons, cloud belts.
now I will put a disclaimer there. If you want to look at the sun, you need to put out a little more money because you don't want to trust some of these cheap optics that they say, oh, they're filtered for the sun. You don't want to trust your eyes with that. You want to get something from a reputable source.
Well, those old telescopes would have solar filters in the eyepiece,
Right.
which are bad because all the sunlight's being focused right at that eyepiece. You do not want to use eyepiece solar filters. You want to use a filter that goes over the end,
Of
the front end of the telescope.
You want to block the light before it gets down to a focus.
Yeah.
That or we ought to do a whole show on that sometime because there are ways that you can actually project the image onto like a sheet of cardboard or something, and that won't burn your eye. I just don't want people going blind because we suggested something and they said, well, let's try that on the sun. So, shall we take a look at the spring sky?
Yeah, we'll take a look at the spring sky.
All right. So here's our spring sky.
So, and now this is a little different than what I did if you saw my last time I was on this podcast with the winter sky, because a lot of that was stuff you could see naked eye or with binoculars. A lot of these are going to be telescope objects. And so obviously there's a lot of stars in here, but I'm going to talk a little more about some of these objects that I labeled on here. And so, and there's a huge variety of distance. So one of the closest thing on here is this Wolf 359. That's only 8 light years away, and that's a red dwarf. I put that in because I know a few podcasts ago you talked about red dwarfs some, and so this is a red dwarf star. I'm actually going to talk a little more about that, but we'll kind of go through some of these other objects first, and then everything else is really far away. So up on the top, underneath the handle of the Big Dipper is M51, the Whirlpool Galaxy. That's about 20 million light years away. So that's outside our galaxy. Everything else here is, that's circled is outside of our galaxy. Then there's the Virgo cluster. That's the nearest galaxy cluster to us. And that's about... Now there's a range. I put 60 million, but there's galaxies that are 40 million. There's ones that are further out because it's a big cluster and it's tens of millions of light years across. So There's a coma cluster, so lots of galaxies. The spring sky is galaxy time. If you got a big telescope that can see galaxies, there's just you'll be out every night.
And don't fret, we'll be showing you some of these galaxies in a minute, and you can see what we're talking
Yeah.
about.
So coma cluster, that's even further away, and then I put a quasar, that 2.4 gigalight years. That's 2.4 billion light years. So a big range. So I know part of this podcast is putting Robert on the spot. I've known you long enough. I should know your name by now.
It's all good.
So
It's not the first time I've been called Roger.
So I'll ask you, which one of those objects that I labeled on there do you think is the faintest apparent magnitude?
Faintest apparent magnitude. I'm really not sure about Wolf 359, but if it's an M dwarf, it's pretty faint. But I also know, having looked at the Virgo cluster myself, that it's, other than a couple of objects in it, it's pretty faint. But I'm still going to go with the Coma cluster.
So the brightest galaxy in the Coma cluster, magnitude 11.3.
Okay, that's pretty dim.
Wolf 359, magnitude 13.5.
I should have gone with my first instinct. Rats.
So if you go by the brightest galaxy in the cluster, the faintest object that I labeled on here is the closest one. Wolf 359, a red dwarf.
Yep.
And I always find that amazing, and I think you talked about this in other podcasts. Red dwarfs are the most common star in the galaxy. You go out on a dark night and you look up, you don't see a single one.
Right.
At least the M dwarfs. I'm not sure about Ks, but I don't think you don't see any M dwarfs.
I think you see a few K giants, but I'm not sure about K dwarfs.
Not the dwarfs. I don't think any are naked eye. So yeah, the most common star in the galaxy, you can't see any of them with your eye, and that always amazed me.
Let me slip one thing in here, because we talk about magnitudes. The magnitude scale is a brightness scale. With a naked eye in a dark sky environment, I mean, well out away from the cities and everything, the human eye can detect down to around. By the way, the bigger the number, the dimmer the object. So in a dark sky, well away from the cities, the average human eye is able to detect down to around magnitude 5. The Wolf 359 that he was talking about was magnitude 13. And it's a logarithmic scale at that. So it's not just a matter of Wolf 359 is twice as dim as the dimmest object you can see. It's,
every 5 magnitudes is 100 times dimmer.
Right.
And so,
That's a full, let's see, what's 100 times 100? 10,000 times dimmer than you can possibly see with your eye.
It's very, very faint. In fact, it's not even a binocular object, not even a small telescope. This is a medium-sized telescope. You're probably going to need like an 8-inch telescope.
Yeah.
To see this. I've actually seen all the other objects in here. I took a picture of Wolf 359, but I have not seen it visually. I could,
right.
but I just haven't bothered.
Right.
Well,
I will say with a 24-inch telescope, because I did in light polluted suburban Atlanta skies, I did a limiting magnitude test with a 24-inch telescope, and with a 60-second exposure, its limiting magnitude was about that 13th magnitude through a blue filter.
Oh, okay.
So we're talking a 24-inch telescope with a relatively short exposure time, 60 seconds, would still have trouble picking wolf out.
You must have had some light pollution.
Oh, yeah.
Yeah. Okay.
It was suburban Atlanta.
Because you should be able to see fainter than that in a dark sky.
It was suburban Atlanta. Now,
okay.
Through the V filter, it was more like magnitude 16.
Oh, okay.
So it's that really deep blue that's the problem. But still, that's pretty impressive when, a 24-inch telescope with a
would have
certain
a
filter
hard time
would
seeing
have a hard
that.
time
Yeah,
seeing it.
yeah, and it is. I mean, this is relatively nearby. So as far as stars go, we got the Alpha Centauri system, and Proxima Centauri is the closest star to us. It's also a red dwarf. It was only discovered in 1915.
Right.
The closest star to us, we just found out about a little over 100 years ago.
There you go.
Because it's so faint. It's brighter than this one, but
And
faint.
to put a little bit of comparison, because I happen to know this, the dog star Sirius down here in the southwest, low on the southwest horizon, is about 8.8 light years away.
Yeah.
But it's the brightest star in the seen from Earth.
Right.
So
about the same distance.
About the same
A
distance.
little bit further. Yeah.
But it shows how varied these stars are, because Sirius, if I'm not mistaken, is a B, type B.
I thought it was A.
It may be type A, yeah.
They're close, but yeah.
So, Sirius, in other words, is a big, hot star compared to Wolf 359, which is a tiny red star, giving off just a very small amount of light compared to the big bonfire that is Sirius.
Yeah. And I think the ranking we got at the Alpha Centauri system,
Yeah.
then there's Barnard's star, which is another red dwarf, and then Wolf 359, it's like the third one out.
And you can't see it.
Yeah, you can't see it. So, yeah. So, and it kind of gets into what we see is not the most common. When you look in the sky, you see a lot of giant stars, but those are rare. We see a lot of them because you can see them from so far away. So
Right.
we'll see giant stars, 1,000 light years away. Where these faint ones that are less than 10 light years away, we can't see at all. And we didn't even know about them until telescopes.
Right.
So Wolf 359 is known for a couple things. One, if you search for it in Google, you will find lots of results about the Battle of Wolf 359 from Star Trek.
Right.
In fact, the Borg attacks it, and most of your search results will be that. So when I was trying to find the next thing on here, you have to put in Wolf 359 and then like parallax or something to find it.
So you ready for that slide?
So
then?
we can go to the next one.
Okay.
So this is these are two pictures of that star taken from two locations, Earth and then the New Horizons spacecraft. And the New Horizons spacecraft was about 40 billion miles from Earth. So it's about 40 astronomical units where an astronomical units is the distance between the Earth and the Sun. So, and this is how we find the distances to stars. So I labeled these distances. Most stars, this is how we get the distance, is through parallax. And usually the example with parallax is you hold a finger in front of your face and you blink your eyes, and if you look at your finger with your left eye and then with your right eye, the finger moves back and forth. And as you move your finger further away, it moves less. And so what's happening here is most of these stars are much, much further away than Wolf 359, and they don't move. You look at them from Earth, you look at them 40 million miles from Earth, they look the same. They don't look like they move. But that one star moves back and forth. And so this is basically how we have depth perception. We have two eyes, and the view is slightly different in both eyes. And so this was like having two eyes, 40 million light years between the
40
eyes.
million miles.
Or miles, not light years.
Yeah.
Got used to the light years.
Yeah.
I knew I was going to make that mistake. So imagine you have two eyes that are 40 million miles apart from each other. You have pretty good depth perception. But even then, only that one star is actually noticeable as being closer than the others.
But this is an example of how we know by that shift in distance, we can tell the angle of that triangle. And so as I've tried to describe to some people before, either geometry only works here on Earth, or that star is 8 light years away.
Yeah.
It's one or the other. And this we're getting better at determining distances with this parallax, because we're getting better optics so they can tell smaller and smaller.
Yeah, this is a challenge. And so now this is not normally how we do it. This was a neat experiment done. The New Horizons is the spacecraft that went by Pluto, so
Right.
it was a long ways away from Earth. So it was a neat experiment. Typically this is done as Earth orbits the sun, and we really just have the distance of Earth's orbit, the diameter of Earth's orbit.
Right.
And now we've had the Gaia spacecraft. Its main job was to get parallax of stars, and so we now have the parallax and distances to 1 billion stars. And so we have accurate distances to 1 billion stars. That's not... In one way, it's mind-boggling that it did 1 billion stars. I can hardly believe it. And then on the other hand, that's less than 1% of the stars in our galaxy.
In our galaxy, right.
So we barely made a dent in mapping our own galaxy.
Right. So still plenty to do out there, folks. Those of you who are younger and might be interested in joining us doing this type of work, there's still plenty to be learned, still plenty to work on out there. So yeah, but this is what I was always taught, and what we call the first rung of the distance ladder, because this is a direct geometric measurement of how far away things are. From there, if we get some other things going for us, what we like is an overlap. We get its distance measured this way, and then we use the other method to measure it. If we get the same answer, hey, that we can step up to the next rung. And one show we'll probably do a discussion
do the
on
whole
the distance
thing.
ladder.
Yeah. So this is the first
This
step.
is the first step.
And if we can get distances to certain types of stars, and we have an idea of how bright those stars are, well, then if we find those stars in other galaxies, then we can work out a distance to those galaxies. And so that's kind of how it builds up.
That's how it builds up. Yep. So I love this picture.
Yeah. So
this is not a pretty one or anything like that, but what it's showing us is really important and a really big deal.
It's really the only good example showing parallax of stars, because we don't normally have this big of a baseline for the images. So
wouldn't that be nice though? Just send out a telescope to Pluto orbit to just do baseline for astrometry. This is called astrometry, by the way.
Yeah, do a few more. Now it did this one, and then it did Proxima Centauri.
Okay.
I showed this because we can see it from the northern hemisphere.
Right.
Proxima Centauri we can't see from up here in North Dakota, so you got to go further south. So
got to go pretty far south, because I don't remember anybody ever talking about being able to see it from Georgia either.
Yeah, I think you got to go quite a ways south. I'm not sure if you have to cross the equator or not, but nowhere near. I don't think the United States you can see it.
Interesting. All right. So what do we got next?
Well, next, since these red dwarfs are so difficult, 13.5 magnitude, that's not even a small telescope, right? That's a fairly big telescope. So I did want to show how you can find a dwarf in a small telescope. And now we have to, play with the definition of red dwarf. Usually when we talk about red dwarfs, we're thinking of M class, the spectral M. And so, and people probably don't have it memorized, but there's O, B, A, F, G, K, M in order from hot to cold. The sun is a G, and so the only ones that are cooler in the sun are K and then M. And so the M dwarfs are all really hard to find even with a telescope, but there is a K dwarf that's fairly easy, and it's in Cassiopeia.
Okay.
So if you go out and you look for Cassiopeia, I have a little circle around it. It's not one of the main stars of the W, and that star is not the K dwarf. So, but it helps you. It helps you find it. So now that star is Eta Cassiopeia, and that's interesting on its own. This is very similar to the sun. And it's about 20 light years away. So it's kind of neat. If you want to see what the sun would look like from 20 light years away, you can go find Cassiopeia. It's in the northern sky. This time of year is kind of low in the northwest. And it looks like a W.
I was about to say that W or M shape is real easy to spot in the north.
So it's usually people once you know it's in the north, you look around, you can find the W or M or E or 3, depending on the season.
Depending on the season.
So, but you look for the W shape, and that little star there is kind of off, from the main stars of the W, but it's about 20 light years away, a little bit less, like 19 and a half. It's a sun-type star, so it's kind of neat to see what would the sun look like from 20 light years away. Not very noticeable. Naked
Right.
eye from a dark sky. This might actually be tough to see from town.
Yeah.
But from a dark sky, it's actually pretty easy to see. Now, if you take a small telescope and you look at that star, medium power, like 100 power, you'll see a little red star next to it. It's a double star. And so this
Okay.
sun-like star has a K dwarf. It's a K7, I think. So it's on the lower dimmer
mass
end.
size of K. Yeah.
So so it looks red, and so you don't need much. You find this star, which is naked eye, at least in a dark sky, small scope, and you'll see a yellow star and a red star right next to each other. It's kind of pretty to look at, and it's kind of neat to know, hey, that's a sun-like star with a red star,
A
a
slightly
little
smaller
dwarf.
companion.
Yeah,
Yeah.
about half the size that orbits it. So it's kind of a neat thing to, and it's bright enough that even with light pollution, telescope won't have a problem seeing it.
Right. And let's see. I guess we've mentioned the spectral type before, but I don't think we've mentioned the fact that along with the spectral type, OBA,
FGKM.
FGKM, there's a number between 0 and 9 that's associated with it. And the 0 is the largest mass of that class, and the 9 is the smallest star of that class. So a K7
Yeah,
is a pretty low mass K star.
yeah.
So
So this is probably the easiest red dwarf. It's not an M, but it's close
Right.
enough. So
you can see it. That's
yeah,
the important
so you
part.
can see it in a small scope. You don't need to get a big giant scope out.
Right.
Yeah.
So that's pretty cool in and of itself. All right. So next we wanted to look at, I guess, booties.
Yeah. In fact, go to the spring sky so we can see
Oh, okay.
movies in it, just
So-
so where it is. So there's this little rhyme we use to find Arcturus, and way on the top is part of the Big Dipper anyway. And there's a handle there. The handle of the Dipper, there's this arc, and if you follow the arc, it arcs to Arcturus. So this is a rhyme we use to find Arcturus. And so Arcturus itself is kind of interesting. It's kind of like Aldebaran in the winter sky, in that it's roughly the mass of the sun, but a lot brighter. This is a red giant, similar to what the sun will end up being. And comparing that Eta Cassiopeia was about 20 light years away.
Right.
Arcturus is about the same mass. It's 40 light years away, but
But
much brighter.
Much brighter.
So,
yeah.
kind of if you watch my winter sky thing, we talked about this a lot. So this object is twice as far away, but much brighter. And this is a thing you can go out, and it works better to go out and actually look at them. Look at the Eta Cassiopeia. That's the sun at 20 light years. And then Arcturus, the sun as a red giant, twice as far away, but much brighter. Like
Now, let's
even the light
put it in
pollution.
perspective. The sun will become a red giant in about 3.5 billion years. So we've got a little time.
We got a little time, yeah. So, but I like to find, stars that are kind of like the sun. We can kind of see, hey, that's our future.
That's our future. You're
So, Arcturus would be a similar red giant to what our sun will become.
cool.
So,
And yeah, there's another part of that rhyme because we arc down to Arcturus from
Yeah.
the handle of the Big Dipper, and then you can speed down to Spica or Spica
yeah,
in Virgo.
yeah. I always heard it as spike to spica.
Spike to Spica. Yeah.
So,
There's people always used to ask me in observations, how do you know where all this stuff is? And it's like, one, practice. Two, there's these little mnemonics, these little rhymes or sayings that you just learn. Okay, that's the Big Dipper. So there's Arcturus. So there's Spica, and so forth. And you just build up a knowledge base of, okay, that must be this star.
Yeah, you work your way out. You find something easy to find, and then you kind of work your way.
Right.
So
Like out in the spring sky, if you look over here to the far right, you can still see Orion. So if you can find Orion, you can find Sirius, which is the brightest star in the sky. And then from there, you've got Procyon above it, and uh, 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 what are the
Castor and Pollux.
Castor and Pollux
Yeah.
in Gemini. So yeah, it's just a matter of learning where a few things are, and then you slowly build up that base to expand outwards from there. And of course, you don't need to be, losing your mind and forgetting the words. So anyway,
And if you are watching, around when we're broadcasting this, Mars is out, and you can see that in Gemini.
oh
up
yeah,
there.
there it is.
So Mars is still out. I think we moved quite a ways from it, so the telescope is probably small and doesn't show much,
Well,
but it is visible in the sky still.
That's always one of the things that those night observations I mentioned. People always we see Mars, and it's like, yeah, but you're not going to be that impressed with Mars
Yeah.
because Mars is a red dot with your eye. And through a small telescope, Mars is a red dot. It
Yeah.
really doesn't improve much until you get into really big telescopes where you can put some high magnification.
Yeah, usually you want at least 200 power.
Right.
And you can, if the winter part is tilted toward us, because it tilts like the Earth, you can see the polar caps pretty
Mhm.
easily on Mars.
So, but for a 200 power magnification, yeah, you're going to need about a 6-inch or 8-inch telescope for it to be clear. If I'm
Yeah,
remembering correctly.
yeah. I think I guess the main scope that I started with was a 6-inch.
Okay.
So, and I was able to see polar caps on
Okay.
Mars and stuff in that.
The issue I'm talking about there is you can overpower a telescope. If you get too high a magnification, the telescope basically isn't collecting enough light, and so you get a blurred image. And
Yeah,
it really doesn't help your viewing enjoyment.
I think the rule of thumb was 50 times the aperture in inches. So a
Sounds
4-inch
right.
telescope you could push to 200. And
But
that's
you're
really,
pushing it. You're pushing it.
yeah, you're pushing it. So, so 4-inch really would be the minimum for a good view of Mars. Now that'll be fine with Jupiter and Saturn.
Oh, Jupiter and Saturn, you don't need. Yeah,
50 power will show you Saturn's rings.
right.
Yeah, Mars usually you want to get the power up more.
Yeah.
So
Going back to booties.
oh yeah, booties. Oh yeah. The other interesting thing. So Arcturus is interesting because it's like the sun as a red giant, and it has a high what's called proper motion. The stars aren't really fixed, so they can appear to move because of parallax, but that's really small change. But they also have what's called proper motion. They're moving through the sky on their own paths. And Arcturus is fairly close at 40 light years. It actually has a higher than average proper motion. So this is just a simulation showing booties now and then showing booties in 20,000 years. The shape has gotten pretty strange. And the thing that has changed here is Arcturus. Arcturus will move quite a bit in 20,000 years. And so that ice cream cone shape is how I think of booties as an ice cream cone. So, or a kite. So
it becomes more of a bacteriophage.
so yeah, it's gotten really stretched out. So so it has a high proper motion. It's kind of passing by our region
On its
fairly
way to
quickly.
better pastures. I mean, that's pretty neat. And if you look at the diagram closely, there are a few other stars that are moving pretty well as well. But I got to admit, until the show, prepping for the show, I hadn't realized Arcturus had that high a proper motion. It's unusual. Most stars have very small proper motions, so it's kind of unusual. So that's kind of neat. So next, I think you wanted to show us some.
Oh
of the
yeah, so I
Virgo cluster.
wanted to get it out of go to those further objects. So one of the things in there was the Virgo cluster, and so the Virgo cluster is the closest galaxy cluster to us. So we think about the scale of things. we're in the Milky Way galaxy, and then we have our local group. We have Andromeda Galaxy and M33, and then a lot of empty space.
A lot of empty space.
There's a few, so I did mark that Whirlpool Galaxy on there. That's about 20 million light years. And I'm not going to talk much about that, but I put it on because it is a good, if you got a medium-sized telescope, is a good target. A lot of empty space, and then we got the Virgo cluster, and it has a big range of distances, but that M87 I marked, that's about 60 million light years away. Now this takes up a big chunk of the sky, and it's actually, you usually don't see telescope images of the Virgo cluster. If you do, it's a little tiny piece of it.
Right.
And if you want to see a lot of galaxies, I think the most I've seen in a telescope was around M86, and you see 3 or 4 galaxies.
Right.
But that's a little tiny piece of the Virgo cluster. In fact, this picture is a piece of the Virgo cluster. It's cropped. And so this is not a telescope picture. This is a camera, DSLR, with a 135 millimeter lens on it on a tracking tripod. And so just taking multiple long exposures and building them up so I could get a bigger view. So I did this a couple years ago, partly just to see if I could get a picture of a galaxy cluster without a telescope.
And you really got to do it to understand that's such a common thing. Can I do this? Can I capture this? I have yet to, in all the imaging I did for about 10 years, I was still never able to catch the Witch Head Nebula.
Oh, yeah.
But I tried and tried and tried, just was never able to do it. So a lot of times you're sitting there going, I wonder if I can catch this. And you try something.
Yeah, you try something, sometimes it works out. And so this worked out pretty nice. And yeah, trying to think about it. This is nearby, which is why it takes up so much space in the sky. If you want to find it, this is actually, most of the things that I circled on there are hard to find. If you point your telescope in that general region of the sky, and I used to do this for fun. I had a manual telescope, and I would just point it to that general region of the sky and kind of just move it around by hand, and I would find these fuzzy smudges.
Right.
I didn't necessarily even know which galaxy it was, but I would just find these fuzzy things in the sky. So you can actually just scan around with a telescope and find these things because there's so many of them.
I will put it this way. I did just a quick search when setting up these slides and counted a double dozen, so 24 of these galaxies just doing a cursory, real quick look by eye. There are at least 24 galaxies in this frame. So anything that looks like a fuzzy smudge, that's probably a galaxy.
Yep.
Now, M87, if I'm remembering correctly, is also about the most one of the most massive galaxies that we know about.
Yeah, I didn't write down the numbers, but yeah, it is a very massive, large elliptical galaxy, and a lot of galaxy clusters will have a large elliptical galaxy that we think basically grew by merging with other galaxies. Eating them. We actually call it galactic cannibalism. So astronomers are kind of weird like that, but yeah, we'll actually talk about galaxies eating other galaxies. And so there's usually a large elliptical galaxy like this, like M87, that has just grown bigger because the gravity just pulls in other galaxies. So it takes up a large part of the sky, and it's part of the Virgo supercluster, which technically we're a part of. Our local group is on the edge of the Virgo supercluster, so we're gravitationally linked to all these galaxies here.
That's kind of neat when you think about it too, because they're so far away. You would think, oh, they've got no effect on us. Yeah. They do.
We're part of this structure.
We're part of this structure, yeah. And so, yeah. I don't know what else to say to that. But this can be very entertaining. And, yeah, I can tell having imaged M86 and the M87 through 14-inch telescope, there are literally hundreds of galaxies just right around them.
Oh yeah.
So this is a galaxy-rich field if you start focusing in on particular regions, particular targets. There are just hundreds of galaxies in this frame, in reality. Now, being able to see them,
Yeah.
you probably need a closer in, higher magnification, higher resolution image to really pull them out. But this is a nice target through a reasonably big telescope.
Well, and this is all in 3D. And I was going to mention that M87 is about 60 million light years. I think M86 is about 50 million. So it's actually 10 million light years closer. So there's actually a lot of distance between some of these galaxies. So they're not all the same distance away.
That's cool.
I think we can zoom in on M87. So M87 is the most well-known one. And why is it well-known? Well, it's a giant elliptical galaxy. But for a long time, there was this jet. And so it's known for having this jet of material coming out of the galaxy. And on the left is a picture I took. The jet actually isn't all that challenging to get in a telescope. And so...
Wayne's asking a question. Wayne's apparently tuned in.
Oh, are there clusters of clusters? Yeah, there's super clusters.
There are clusters of clusters. We call them super clusters, yes. And so that's pretty neat. Yeah, we don't reach, astronomers don't tend to reach very far for, what do we call that? Well, it's a cluster of clusters. We'll call it a super cluster.
So, yeah, and we're part of it.
And we're part of it.
Our little group. So the one on the left is my picture. And then the one on the right is zoomed in with Hubble showing that jet. So this is well known. This jet's been known for a while. It's not too difficult to get. I've never seen it visually, but I've been able to image it fairly easily.
Right.
So and so then for a long time, why is there this jet? And the main hypothesis was that there was a giant black hole in the center of the galaxy powering the jet, and people were so sure of it that they went and took a picture of it. And so you probably saw this picture. We can probably go to that. So the one on the left you probably saw from a few years ago. This was that Event Horizon telescope. It was basically a global array of radio telescopes, and they gathered data from the center of that M87 galaxy, where that jet is coming from, and we're able to get an image from it. Now this is complicated because it was a lot of different telescopes. One of them's in Antarctica.
So you've got to calibrate not just for the different telescopes, but for each instrument, for the noise in the instruments and everything else. Yeah. This is not an easy process.
So it took a while.
Right.
Gathering the data. They actually had to ship hard drives of data from Antarctica. So it took a while to analyze this. But they were sure enough that there was this black hole that they went through the trouble. And so this is where that jet comes from. Is this black hole? And that's the picture on the left. And just fairly recently, I think just a couple days ago, I saw some news articles with the updated higher resolution version. And so that's the one on the right. So this is fairly new. And so this is a reanalysis of the data using artificial intelligence, which is all the rage now.
All the rage.
Or maybe machine learning.
How good it really is, we'll see. But.
Yeah, so the idea is they're trying to fill in missing data. So they're using machine learning that was trained on simulations. The thing with machine learning is you train it with lots and lots of data. Well, there's not a lot of real data to train it with. So they trained it with simulations to try and fill in the missing data. And so we do have a sharper view here. And that ring probably is very thinner than what we see here. And so that's kind of our new image. And yeah, we're both a little skeptical about
The AI,
filling in missing data.
right?
So,
Especially with simulations. I mean,
yeah,
I'm what's termed an experimentalist. I believe in getting real data, not necessarily, but I'm not going to knock on those guys too much because what they do is good work. But something like this, show me some real data, like the one on the left. But now I will point out that we're not seeing the black hole because that's something I've noticed a lot of people
Right.
jump on. You're not seeing the black hole. You're seeing this disk of really hot material because as it falls into the black hole, it gets moving faster, spins faster and faster and faster, which means it's hitting each other at higher and higher speeds, which if you'll remember our discussion, the faster things are moving, the harder they're hitting each other. That's what we say is temperature. So this is the hot disk of material that's falling into the black hole. So what you're really seeing is that ring, that disk, and the shadow of the black hole on the
Right.
disk.
And the actual black hole probably is not the size of the black,
Yeah.
the actual black hole that you see as like a gravitational shadow.
Right.
Because the light that gets closer in ends up not getting to us.
Not getting to us. It gets curved and shot off in all different other ways. Right. So keep that in mind. It's not that we can actually see a black hole. So they're not really black. Yes, they are. But what we're seeing is this hot gas and material around it, and it's casting a shadow onto it. So, yeah. All right.
So the last thing I had marked on that spring sky map is this Quasar 3C273. And now this, I should mention, you're not going to easily find this.
No.
I have seen this. I saw it in a 12-inch telescope. I think you could see it in a smaller one, but that just happens to be what I was using. And it's a challenge. And the thing is, quasars, that means quasi-stellar object, because they look like stars.
They look like stars.
And you look at this in a telescope, it looks like a star. You don't scan around, look like the Virgo cluster, you could scan around by hand and find a fuzzy thing in the sky. This won't look special to you. You basically have to have a map showing you all the stars in that region, and then you look in the eyepiece, and you look at the map, say, okay, I see that pattern of stars there, and
Yep.
okay, I think that star there is the quasar, because it looks like a whole bunch of other stars that all look the same. So this just looked like a star. But then people went and they got the redshift of it, and redshift is one way we get distances to galaxies, and it comes from the expansion of the universe. So because everything is moving away from us, there's this redshift, and they did the redshift on this quasar, and it was a really high redshift. Like, this looks like a star in our galaxy.
When they first started discovering this, they thought they had to be in error. They really did. They thought it had to be wrong because this is a star.
Yeah.
So it can't be that high redshift.
Yeah, stars in our galaxy aren't moving away from us at that high of a speed.
Right.
So it turns out this is not a star. This is really far away. In fact, it was, I wrote on there about 2 billion light years away, a little more than 2 billion light years away based on the redshift. And so this was a mystery for a long time. What is this? And we found these other quasars. There's a bunch of these. What are these things? Well, finally we got good enough instruments. And so the one on the left is kind of just a normal Hubble image. And it looks like a star. The one in the middle, they were able to block out the central light, and it turns out there is a galaxy there. What we're seeing is that the quasar is really the central part of the galaxy, and then the one on the very right, bottom right, there's a jet, and that's X-ray, but the jet also shows up in other wavelengths. This basically is a lot like M87. There is a giant black hole in the middle of this galaxy. But this one is way brighter than the one in M87. So there is a jet just like M87, but it's so bright. And now the black hole isn't bright. It's the material around the black hole. It's so bright that it overwhelms the galaxy. And so for a long time, that's all we saw. was the light from the center of the galaxy.
If to put it in perspective, if M87 were feeding as hard as this galaxy is and were therefore as bright, we'd be able to see it in the daytime sky, if I'm not mistaken.
I never actually looked into that.
I think I heard that once, that it would, the M87 would be
It
bright
wouldn't
enough.
surprise me. It would be naked eye anyway.
Yeah, it would definitely is naked eye bright, but yeah, I think it's bright enough that it could be daytime bright.
Yeah.
So this is a bright object.
Yeah, and we were only seeing the very center, and it just overwhelmed the galaxy, which why confused people because it just looked like a star.
Right.
But there actually is a galaxy there, and a giant black hole with a really bright,
Bright
hot
of
disk
material
around it. Yeah. So. And it is possible, but you need a pretty good sized telescope. But again, this is brighter than Wolf 359, the red dwarf, that's 8 light years away from us. This is easier to see. It's easier to find than that red dwarf.
That's impressive.
So,
yeah, it just gets into just how bright some of these things are. So, there we have a trip around the sky here in the spring. So I'm going to go back to that slide for real quick.
yeah, so you can see where these things were.
So you can tell where these things are. So we talked about the Quasar 3C273. We talked about Wolf 359, the Virgo cluster, and we didn't look at Coma cluster or the M51, but the Coma cluster looks very similar to the Virgo cluster.
Yeah. Now Coma cluster is 5 times as far away.
Right.
So it's a lot smaller, fainter. I've seen a couple of galaxies. It actually has 2 large elliptical galaxies. Okay. And I've been able to see those visually, but it's a lot harder. Because it's a lot further away.
A lot further away.
But yeah, probably the only thing here that, Virgo cluster, you can find at least a 4-inch telescope. Probably better to have a 6-inch telescope. In fact, the way I find it, if you look at Leo the Lion, there's the back star of Leo the Lion, and I just and then there's this the kind of top star off of Virgo. I just go halfway between there, and if you got a manual telescope, I just kind of point in that region where that circle is, and there's fuzzy galaxies.
You're going to see them.
Yep.
That whole region, you're going to see galaxies. Yeah. So.
Everything else, you're going to need a map.
That or just a lot of time going out and finding these
learning
things and becoming experienced at it.
M51 isn't too bad. It's right under the handle of the dipper. I do need, I kind of know the stars in that region to find it. Mm-hmm. But that's probably the next easiest object would be M51. So
easy. Put that in.
Still at least probably a 4-inch telescope. I'm guessing. Most of my experience was with 6-inch and bigger. So
I gotta admit, finding things like M51 and everything, I relied on the little push buttons on the motor control.
So
because
for a long time I had a 6-inch Dobsonian.
Okay.
And so I used that for about 10 years before I got a go-to. Yeah. And so I learned how to find all these things.
I had one of our student assistants that was able, like the Ring Nebula. I mean, he'd just drop the telescope, go, there. And, in a matter of half a minute.
Ring Nebula's pretty easy.
He's found it. Me, I'm sitting there swinging the telescope everywhere, going, okay, how did you do that? So, it takes practice and it takes a certain amount of just learning where things are. So, but that's our spring sky coming up. In fact, this is for a date of 4/17.
Yeah, so I put it for, I guess it was last night I was making this. Okay. So it was last night at 10 p.m.
Yep.
It'll look the same tonight.
There you go. And it'll look about like this for probably the next 2 or 3 weeks before there's a significant change.
Yeah. Everything's going to kind of move more toward the south. But a lot of this you can see all through May and even into early June.
Yep.
But then it'll be moving into the west.
You'll lose all this stuff on the west. Keep that in mind. Yeah. So Orion's about to go into the daytime
Winter's
sky.
going away. Spring is coming up.
Spring is coming. So.
And then the summer is way off on the left side. There's Hercules way on the upper left, but we'll leave that alone.
We'll leave that alone. Maybe we'll talk about that this summer on a broadcast. Quite likely. All right, and so to wrap things up, I'm going to talk a little bit about a recent finding from James Webb, and that is James Webb targeted a planet that we knew about that orbits a red dwarf binary. Or actually, one of the stars is an M dwarf, one of those red dwarf binaries that we've talked about, like Wolf 359, and the other companion is a brown dwarf. It's a failed star. And they have a companion that we knew was around Jupiter mass. So we thought it was a planet, but as I'll be discussing here in a minute, there may be some question about that. But it's called VHS 1256. And so here's some information about the stars and about the planet. The stars are located in the constellation of Corvus. Their magnitude 17.6 apparent, so they're even fainter than Wolf 359. And it's the main body, the main star is an M7.5 star. They're about roughly 70 light years away. The planet has a mass of 11.8 Jupiter masses, and it takes 17,000 years
That's a long time
for it to go around that host star. Now, to put that in perspective, keep in mind that Pluto only takes 256, somewhere around in that.
Yeah, I think it's around 200 years.
So this planet orbits really far away from the M dwarf and the brown dwarf. And that's why it became so interesting, is because James Webb should be and proved capable of imaging that planet all by itself without masking out the star's brightness, which also means it was able to directly get the spectra. Normally, when we get the spectra of an exoplanet, we have to take the spectrum of the star, and then when the planet goes in front of it, we can factor out the normal spectrum of the star and get the spectrum of the planet's atmosphere if there is one, because whatever absorption is left must have come from the planet, right? Seems reasonable, right? So with this one, with VHS 1256, the issue is that the planet is far enough away from the stars that we could directly, with James Webb, look at it and get the spectrum. So what did that spectrum look like? Well, there it is. So we saw water in its atmosphere. We saw carbon monoxide, methane, and silicates. That means this atmosphere is full of sand. It could be anything from little dust grains to sand grains like you'd find on the beach, which led to them actually looking at the temperature, and the temperature is over 3,000 degrees Kelvin. So it's got a temperature roughly of a star. So as small as it is, only about 11 Jupiter masses, it sparked a discussion of, is this really a planet or is this a brown dwarf too? And so there's still things to learn, still discussion going on about this. But to me, it's just really neat because we've talked about spectra and how it's the workhorse. This is how we know things are there. So we look at the spectra, and everywhere these little dips, that's the fingerprint of some molecule or element or ion, if it's hot enough to strip away electrons. And so this is a fingerprint that tells us what is this atmosphere made of. And, we just, like I was saying, we don't get the chance with planets to do it directly. We have to let it pass in front of the star because the star is so bright comparatively that it just glares out everything around it. And that's why it's so hard to image a planet around another star too, is the star just glares everything out. So that was the neat thing that I'd seen in the news recently and was like, this is so cool. But I'm the planet guy, so.
I'm guessing we'll get probably more.
We will.
This is the first now.
This is the first.
Yeah.
So willing to bet that there's plenty more targets that they have of interest of this type. So I'm betting that we'll see more of this type of thing going on. I'm betting we'll see. James Webb has already proved that it can get the spectra of a planet going in front of its star. So I think we're going to start seeing a lot more of this type of thing, and therefore getting a lot more of, hey, this is what the atmosphere of these planets are like. And so Wayne asked another question. Is it true that when you get a new telescope, it will be cloudy for 2 weeks? I don't know if that's scientifically testable, but it sure does seem that way.
Yeah, and I think it's not just telescopes. If you get a new camera or any kind of accessory,
I remember, like I said, back when that 10 years I was doing imaging, I got determined because I was at home and therefore had access to the university's observatory for a lunar eclipse. And I was determined I was going to get an image of every 30 seconds of that eclipse so that I could put it together as a movie, right? Yeah, it was cloudy. I still managed. I got up to 33-minute exposures and was still able to see the moon through the sky, through the clouds. But I was taking 3-minute exposures to get it done. You couldn't tell that there were clouds. It was really neat. But anyway, we're getting close to running out of time here. So anything else you want to say before we close out, Dean?
I think I covered everything I wanted.
Okay.
Do you ever do any of the YouTube bagging?
The YouTube what?
Begging. Like, you got through the end of the video. If you liked it, click the like button.
Click the like button.
If you're not subscribed, hit subscribe.
Yeah. I think we've avoided that, but if you did like the video, please click like. It helps with the algorithm, as they all think they all say. And if you're really interested in what we're doing here, please hit subscribe, which brings up the other point. If you're interested in what we're talking about, if you're interested in joining us, please consider UND. It's a very good school. The climate is getting nice this time of year. So I definitely recommend check us out. Send us emails. We like to answer questions. We like to answer questions online about the topics we're covering, but we'll talk to you about physics in general, about the department, about the school, and we welcome such things. And so on that note, we always end with a quote. So Wayne provided us one before he went to do what he needed to do. And the quote is from Albert Einstein. And he said, "The most beautiful experience we can have is the mysterious." And on that note, everyone have a good day. We'll see you not next week. We'll see you the week after. We're actually going to take a break on the 25th. So we'll see you again on May 2nd and at 3 p.m. Central Time. And we'll talk to you some more then. Have a good day. Bye.